in around us. They have a lot of, they already showed they are very useful, they are very nice. So why we need? Okay. The main problem is in the organic polymer. You remember, I think now you know that organic means we have carbon hydrocarbon, CH like this. All this main backbone will be of C bonding and having hydrogen in the pendant position. So in that case, when on the long period of time, if this material stays in the nature for a long time, what happens? It reacts slowly with the oxygen, and uh, and it loses its properties. Okay, the property of or the application it is used for, it is actually lost after a long period of. So the stability of this compound in normal ambient condition for organic polymer is not so much. Okay, and of course now you understand, like when we have C and H, if we burn it in oxygen, it can produce what kind of gas? Either water, which is not, of course, not toxic, but it can produce carbon monoxide, carbon dioxide, and lot of other gases which can be very, very. If you have nitrogen there, you can have all the nitrous oxides with the. So these are very much toxic. Okay, so destroying them is also difficult. They can easily degrade upon gamma radiation or UV radiation, which is coming from the sun. Also, it is possible they degrade. So, in terms of stability in air, in temperature, in radiation, it's not much for the organic compound. So that's why we were looking for something that we can use for a long time. Okay, that is something like is very nice, like which also can be used for longer period of time, which will not be degrading so easily. So for that, actually, we from the carbon now we have to look to the other elements what we have in the around. Okay, that is why the inorganic chemistry, like the inorganic polymer chemistry, started. Okay, inorganic polymer now is it's very much important. I'll show you that the applications of those inorganic polymers in next slide. You'll see there are so much interesting properties which cannot be achieved through only organic carbon bond. Okay, so inorganic and also one more thing, not only in case of stability, but also if you see the properties, uh, inorganic elements have different valencies. Okay, suppose you take phosphorus can have in +3 +5. Okay, some other metal in transition metals or other metals, we know that they can have different valencies. Okay, different coordination number, and with this they can change. You can change from 3 to 5, 5 to 3, like this. Lot of changes are possible, and with this new features you can introduce into the polymer. But for carbon it was not possible. They only have 4 valency. So see, this is very interesting. Okay, and as this inorganic material can form very stronger bond with compared to the carbon with other elements, they are very stable towards high temperature. Chemicals, they also have very rigidity in their structure. They are very strong. So we can use those inorganic polymers for very high technological applications. So actually, I'll not give much waste much time on the other inorganic polymers, as as we are focus will focus on the ferrocene based polymers. But for the students, as I prepared, like as actually in study, we have to learn some real inorganic polymers. Okay, and if we think about, so I'll give you only 3 to 4 examples of this kind of inorganic polymers. Okay, so if we think about other polymer except carbon, like except carbon containing polymer, first in our mind it comes actually silicon based polymers. Okay, because you see their uses here in the user in the medical purpose, you can see they are used as a artificial limbs, prosthetics. Okay, they are used to build catheters, contact lenses, even like drug delivery capsules. These all things are made of silicons, hmm, polysiloxanes. This polymer in the left side, where we can see SiO, 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 this kind of bonding. And also a lot of application of this kind of polymer having elastomers, adhesives, lubricants, water repellents, molds, cosmetics. And this is actually possible by changing these R groups. Okay, so this R, whatever I am writing here, you can, there are a lot of other possibilities are there. You can introduce a lot of R groups, different R groups. You can introduce some metal, and you can also introduce some chiral material, whatever like you can use, and then you can get lot of other uh, different properties you can get out of this simple polymer. And I think you can look into your textbooks to their. I just wrote here two or three mm, structure, two or three reaction ways, then you can have a look into the textbooks for their preparations. Silicon-based polymer, I would like to say, because I worked a little bit on this in during my postdoc on the polysilanes type of polymer, uh, and these polymers actually prepared can be prepared through like this. This is one technique, whatever is written here, and here I would like to say with polysiloxane and polysilane, that main difference is there a SiO bond, and here Si, like Si bond, okay, like a carbon-carbon, similar. So this is very interesting polymer, and this is the way of preparation here. You can see with sodium toluene, we can prepare with a chloro compound, silane, we can get this type of polymer. And when we get this polymer, actually we find these are the side products we obtain here. And with these side products, actually, we um, we realize that this must be gone through a radical intermediates. Okay, if this product is not being formed, we would not have get this product. So there must be a radical intermediate is there, and which actually uh, giving us finally this product, this polymeric product. And one more way, this is there, that is called dehydrogenatic coupling. So I will mostly today talk about, when we talk about ferrocene polymer, I will mostly give you some details about ring opening polymerization technique and dehydrocoupling or dehydrogenative coupling, like this type of techniques I will talk about. Okay. So this is one dehydrogenatic coupling which is used to obtain this polysilane, what like this polymer. Okay, so this is one method of preparation of this polymer, and one more way is there, that is dehydrogenative coupling. So here we start with a secondary or primary silane, okay, and then we use a catalyst or heat. Mostly in this case, we use catalyst, zirconium-based catalyst or titanium-based catalyst is there. So this catalyst is used to get this. Very interestingly, you can see the side product, like the byproduct in this compound, that is a hydrogen gas. And now I think most of you would be interested to see this hydrogen gas evolution. I think the people working in this area of hydrogen gas storage and everything, it's very interesting to generate hydrogen gas out of a reaction. So we know it can be used as a alternative energy. So we will talk about more this. So here is the cycle how with zirconium catalyst work to obtain this silicon polymer. I'll not go into details. Okay, it is not much actually not much of, to understand. It is we starting with PHSiS3, the primary silane, and then with zirconium it formed cubic structure where we can see metathesis happen and this H2 is going out. Okay, here, and then it this type of compound again bond with another PHSiH3, and uh, we get Cp2Cl ZrH again in the in our reaction mixture, and again like we get this compound, and again this compound now used for the next level of cycle. So by this way the polymer goes bigger and bigger. So these are the silicon-based polymer we just discussed. There are actually lot of lot of other polymers. I think you will study in your lecture, and also in the textbook you'll find how they are divided according to their morphology, their structure, all these things, so that you can have a look. And one more important polymer we will talk about, that is polythiazine. This is very important and interesting kind of totally inorganic polymer with having this kind of structure. Okay, this look like when it is prepared, it is actually prepared from this compound. Okay, disulfur dinitrogen compound. This is a crystalline compound, solid compound, and colorless. And it actually, due to the very strained little bit, it is a cubic structure, not cubic, I'll say like square structure. So that's why it is actually a little bit in strain. So over time, like if you keep it for a long time, it slowly ring opened. Okay, this ring open and connected to another one, and like this, it gives you polymer, and this polymer is called polythiazine. Very interestingly, it has been observed that this polymer totally look like a metal. Okay, but having no metal, only nitrogen and sulfur. This is actually very shiny solid, looks like a metal, and very highly conductive material. Okay, and and it behaves like also a metal, because as we know that if we decrease the temperature, the conductivity increases, and you can see it's so superconductivity at very low temperature, of course below 1 Kelvin, but it has this capability. It gives you an idea that you can, if you modify this compound such a way that it can give you a little bit higher temperature superconductivity. So this is very, very interesting. Okay, of this kind of polymer. So you see that inorganic polymers are extremely useful in getting all these kind of interesting properties. They are mostly used in electronics devices, electrochemical compounds, different optoelectronics devices to build up. So these are very interesting. And in this things like the conductivity is actually one dimensional, or towards this, like from the this way, from SN this way, the conductivity actually arises, is there. On this direction there is no conductivity, and we know that this is due to actually the conduction band of this polymer. If you see the molecular structure, molecular orbital structure, you will see that conduction band of this polymer is very low lying, like they are almost mixed with the valence band, so easily electron can jump. The unpaired electron of sulfur can jump to this conduction band and give a high electron density into the conduction band and give a very nice, like the conductivity is, that's why it's very interesting to see. One more compound we will, that is that we definitely have to tell into this inorganic polymer, that is this compound, okay, NPCl2 whole N. So this is very interesting compound. Okay, it has lot of properties, and and the way of preparation is like this. Okay, so we have cyclic NPCl2 type of ring. It is maybe 6-membered or maybe 8-member ring, and if we heat it, okay, around 250 300 degrees centigrade, this ring is get opened, okay, and as it opened, we get this chain. So I'm talking, actually also giving an example about ring opening polymerization and dehydrogenative coupling. So these two techniques actually I will talk about in details when we will talk about ferrocene polymer. So this, you can see that the structure is like this. There's very much interesting compound, and Professor, I would like to say here that I worked with Professor Ian Manners in University of Bristol in UK there, and the Professor Manners and his supervisor, Professor Alcock, he was mostly, they were doing, he is the pioneer, I'll say, in this area, and they have lot of synthetic approach to get this kind of polymers, and their uses, their applications. So Professor Ian Manners now working in Bristol, he also had lot of work on this chemistry, yeah, and but now he is working also on different topics. Except this, these are the like very known polymers to us. Except this, we have several kind of polymers. This polyoxothiazines, thionyl phosphazines, hmm, uh, and uh, and also like polyphosphinoburens, uh, um, polyborazylines, hmm, polycyclodiborazanes. This kind of polymers are also possible, and they can be prepared with polycondensation method, ring opening polymerization, or using a block copolymerization technique, or some dehydrocoupling. And their uses are very much interesting. Some are used in medical devices, some in optoelectronics, and some compounds can be used as a hydrogen storage material, or can be used as a ceramics material, or they are used as a flame retardants. So they are very much useful, this polymer, compared to our organic counterpart, organic polymers. So now we will actually talk about ferrocene. Okay. So now our topic, which we were actually interested to discuss about today, that ferrocene based polymer. Okay. So I think you must have noted that this is called a ferrocene compound. This is sandwich compound. It has been discovered around 1950s. Okay, this ferrocene polymer, ferrocene, and then after that, when this iron is there and it is connected with eta 5 CP ring. Okay, carbon, carbon, carbon. All these 5 carbons is attached here, and also attached. So we write it like a centroid. Huh? So this ferrocene compound is a metallocene class of compound, and it is very from the beginning when it is been discovered. After that, it shows its very potential, promising, I'll say, like factors, or is application towards many direction. Many direction means not only a electronic device, but also it is been interested to see that these are interested, this ferrocene compound or ferrocene polymers are used in medical sciences also nowadays. Okay. So why we want to use ferrocene, or why we want to introduce our ferrocene into any polymer? Okay, it can be, I wrote here BP type of phosphinoboron polymer, but it can be carbon carbon also, because this ring is behave like a aromatic ring like a benzene ring. So whatever the reactions we know for the benzene ring, okay, the similar type of approach we can use for this CP ring, and we can use substitution. We can use substitute here, we can add substitution here. So we can modify a lot of, we can introduce a lot of properties into this ring, and eventually it goes to our polymer. So actually now, actually we have to always look for introducing new properties into our polymer. Suppose I made this polymer before, BP, only simple like hydrogen here. So now if I have, but that can be in different property. But always I have to remember that I have to introduce some different properties. And how it is this possible? This is possible if I can introduce some group here, different group, or some bonding property I can introduce. Like this way, we generally try to modify a existing polymer and get a new property out of it. And this is the actually our thing that we have to keep in our mind, that we have to um, we have to keep an possibility. Okay, we have to give a possibility to do this type of things. Suppose I have some compound element here which cannot bind with anyone. Okay, which will not bind with any only hydrogen, not with any other element. So I will not be able to modify this polymer. But if you think that you introduce something there, uh, and actually you have lot of opportunity to modify this thing, and by this way you actually have lot of products, lot of things, and lot of products you can play with, and you can get lot of new material, lot of new things you can get out of this. So but that's why if I introduce only one ferrocene here, I can introduce lot of properties here, here, lot of substitution here. We have already a metal. So this metal iron is in a Fe2 oxidation state. So I can I can oxidize it to Fe3. Now I will get a redox activity, Fe2, Fe3, Fe2, Fe3. This kind of redox activity I can get out of it. See, so the interesting factor of ferrocene. So very interesting. And it has been observed that with ferrocene moiety, when it is inside any molecule, it gives a thermal stability. Uh, and interestingly, this metallocene iron, ferrocene, is a nonlinear optical chromophore. What does it mean? This means that this compound can get third harmonic generation or second harmonic generation, which gives a nonlinear optically activity into your polymer. And you can introduce chirality, optical activity also using this substitution here. And many more. Okay, so we'll not, because solubility is there also, because it increases solubility. It can introduce color. These polyphosphinoburens are actually a compound, is like a white compound, colorless compound. But as soon as you introduce ferrocene, it becomes yellow, orange color. So these a lot of other factors are also there. Uh, in case of chirality, I think for the students, I think you must have studied chirality like normal when carbon is attached with four different groups. We have R and S. All this you have noticed, but there's one more different kind of chirality you have to study, that is called planar chiral. Planar chirality. Okay, what is planar chirality? In this plane, in this cyclopentadiene plane, if I attach two different groups, here one P, and if I attach to here with some other carbon, then this compound will become chiral. Okay, this is called planar chirality, and we can introduce planar chirality by introducing different group here. And how this is measured, how we can say R or S, that I will also show you in future slides. Okay. So not only these ferrocene polymers in material science, they are also used in medical science. There are a lot of things. I you can have this book, you can read this book. It is in the, I'll share the slides with you so you can read these books. And there actually you will find a lot of applications. Particularly you can see the structure of those compounds, the uses of those compounds. Uh, now actually we will go slowly. I will just give you some introduction about the history of these compounds. Okay, so how the development has started. Okay, so you have to remember that metal containing polymers become very much key factor nowadays, and this has been started actually in 1955, and the ferrocene was invented, like was discovered first in 1950s, and just soon after polyvinyl ferrocene mm, has been obtained. But the interesting factor is that that time it was not well characterized. Okay, but that time there are no so much instrument was there. People are not so much, but they found that it's some kind of polymer of ferrocene, but was not characterized properly. It has been characterized almost in 15 years later. 20, 15, 20 years later in 1970, 1975, it has been characterized. And after that, you can see lot of other polymers, polysiloxane came. This polyphenol, yeah, this one with siloxane compound. This is came around 1975, 70, 85, something like this. It came then polyferrocenyl silanes. This compound, those compounds like came around 1990s. So a lot of other polymer came afterwards, and nowadays a lot of polymers with ferrocene derivatives is known. Okay, with palladium, platinum, this type of polymer also came around 1979, 1978, like this. So from these things, you now have idea that metal containing polymer, who are the beginner? Beginner is our ferrocene based polymer. Okay, so a very interesting factor. In the beginning, it was been started. So I draw here three structure. You can see the difference between these three structure here. Here is the carbon, carbon, carbon. So it is actually basically a organic polymer. Okay, but I introduced a ferrocene as a side chain. Okay, it is hanging like a pendant. Huh? So we call it as a ferrocene in the side chain. Okay, and here in these two compound, this one actually polymerization is here. So here one and one ferrocene is here again, and like one ferrocene is there, like this is going. So ferrocene, the our backbone is like this. So it is actually ferrocene moiety inside the backbone. So in this case, I'll say you can mostly not say completely this is an inorganic polymer. You can say like it is mostly like organometallic polymer. Metal is there and organic part is there. Carbon is there. So this is in the main chain, and here there is some spacer group in between the two ferrocene moiety. Here is one ferrocene moiety is there, and again one ferrocene moiety is here. Okay, in between two ferrocene moiety there is a siloxane and biphenyl group is there, like to make a spacer in between them. And this definitely you can see from the structure they definitely will show definitely very nice or different kind of properties. Hmm. So ring opening polymerization, you can have a look. So I will what I was talking about that I think I just need to remove this. Okay, we'll keep it here. So ring opening polymerization of ferrocinophanes. Okay. Now this is a As I said you that I will discuss for the ferrocyanopane with the ring opening polymerization and the hydrocoupling technique. Okay, so this is the ring opening polymerization technique of what is used to get different kind of polymers from the of ferrocene derivatives. And for the ring opening polymerization, you have to remember that you have to make a ring somehow. How by anyhow, you have to make a ring which is very much strained, little bit strained. Okay, not a very nice stable ring. Okay, you have to make a ring which is unstable. Hmm. And then as soon as you heat, you give a little bit energy to this ring by some chemical methods or by heating or by any other technique, or also possible through UV radiation. Anyway, anywhere, if you give energy to this thing, it opens up. As soon as it open up, it start polymerization. It open up, and to the next one it hit, and next one is like this. It goes like polymerization. So for that, actually, a new class of compound was prepared, and that is called ferrocenophanes. Ferrocenophanes is actually is joining two ring together. Okay, so see, this is CH2, CH2, CH2 compound with carbon compounds only here. So these are five compounds, and these ferrocenophanes were represented like this. If you have three carbon compound, CH2, 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 you can call it as a like this. Third bracket, three means number of carbon atoms, and ferrocenophane. This two represents one, two, three, one, two, three. Two substituents are there in two sides. So you can call it like in third bracket, you have to give three ferrocenophane. Okay, I think now you understand the how the nomenclature works for this type of compounds. And this compound, we have one, two, three, four, five carbon connector. Okay, so you can call it as a, in third bracket, you can write five ferrocenophane. Suppose if you have a five here and three here, so you'll write it like three, third bracket three, and third bracket five ferrocenophane. Okay, so by this way, or you can, if you have three connector, like then you have to write in third bracket three, 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 and then you can call it as a like this ferrocenophane. But interestingly, till now we there is no example of having only one carbon atom attached. Okay, like one ferrocenophane is not yet, because that would be much more strained. Okay, because here one, two, three is there, five is there. It's not much strained compound. But if you have one, it will give you really like this one ferrocyanide is with carbon, it is not there, but with other material it is there. Okay, see the interesting factor about all those other elements. I gave you some examples here to have a look with tin, silicon, boron, phosphorus, sulfur. We have all those ferrocenophane, that is called one ferrocenophane. Okay, in the third bracket you have to write one ferrocenophane systems. And these there you can see here the ferrocene is almost like straight, but here I wrote it as a like a, making it like a little bit bent, because this they are such a way they are bending it, holding this two ring. It actually helps to bend. So it means it is very clear to you that it is not stable. It is always try to get straight. Huh? So it is not, it is under stress, it is under strain. Huh? So if you hit them or if you give some chemical stuff, anion or cation, it will easily open up. Okay, and it is a very nice you can see in these papers in the there that you can see this ferrocene when we kept in a very like same concentration, it is almost yellow. Hmm. And here this is the with the silicon ferrocenophane, it is like little bit orange, red, more red. So the red shift is there. And what is the difference between these four? I can from this I can say the size. See the size of this element, silicon to phosphorus to sulfur. Hmm. So the size is actually decreasing. Okay, as the with the increasing smaller element, we see the let's see. Okay, so this is actually the color of ferrocene. Actually, I would like to say here that the ferrocene generally shows in UV spectra generally show three transition. Around one is 225 and 330, and one is 440. So this 440 generally we see the color. This is coming into the visible range, and this 440 330 is actually nothing but the Laporte forbidden DD transitions. And the color we see from the homolumo transition from the in the ferrocene group. Mostly they are all near to DD. D character is there mostly for the molecular orbital. They have mostly DD character from the iron, and this transition, these gaps is definitely is influenced by introducing a bend. When we are bending this whole ferrocene ring towards one direction, it definitely this homoluma gap is changing, and we see the result red shift of this compound. Okay. Uh, So, so this ring opening polymerization to obtain the ferrocenophane, we have different kind of process. That is, one is called flycatcher approach, and one is salt elimination metathesis. Okay, so these are actually from this technique. I think you would like to see that, like we see we catch the fly, like the fly is a 2 plus here, huh? The two like a ring is there, and we just catch it. Okay, so what is this? We use a FeX2 type of compound, and having A2 plus with CP rings, and X2 with A2, they go out and Fe come in. Okay, and they form this kind of polymer, and E is the metal or whatever the element is there, sulfur, silicon, or whatever. And one more technique, generally salt elimination metathesis, in our laboratory, like in during my research work, actually we used to uh, use this technique to get this kind of compounds. We use n-butyl lithium and TMEDA to obtain this dilithiated product, and then we use a element with halide compound or something substitution which will leave lithium chloride out or lithium bromide out, and will ultimately give you this kind of strain structure. This is you have to remember that this compound, if you are making some compound, if it is very unstable, you have to, after preparation, you have to take very extra caution to make it stable. You do not have to make it very cold temperature, and also not extremely exposing to the light. It can be polymerized immediately. So from this technique, we synthesized CC, that we use heat or platinum catalyst, we obtain this kind of polymers. Okay, so these are the polymers is obtained in and here I would like to mention one thing, that when you open up, if you use a anion, like suppose in this case n-butyl lithium anion, n-butyl minus, when it come minus is attacking here. Okay, and then it's come electron is coming here, so phosphorus is a negative charge. Okay, so you have n-butyl lithium, n-butyl minus taking the like from here electron become butane gas, and to stabilize it is like lithium plus. And as soon as it became minus, this minus came here phosphorus on the phosphorus atom, this minus again can attack to the next ferrocenophane here, and again it can go off, the bond can break, and it can go again out and make again uh, it is minus. So this n-butyl lithium you can take as a normal catalyst. You do not have to use it as a just as a initiator you can use, and then you do not have to, you just leave it like this, it will automatically polymerize. And but the interesting factor is that at the end of this polymerization technique, you will have this kind of product. This is called living polymerization technique. Okay, living anionic polymerization. Okay, living means it is still alive. Okay, it is still alive for next polymerization. Like this can really hit someone else. So in that case, if you introduce another ferrocenophane with different compound, different kind, so it will again attack here and polymerization will start. So by this way, you can really obtain very controlled way, living very controlled way. You can finish, you can get block copolymerization. You can obtain. Okay, so control on the polymeric polymerization is very important factor. I think you might have, we will discuss about the polydispersity index, which is a measure of measuring the polymers. So with this kind of polymerization technique, ring opening polymerization, we actually get um, mm, this kind of ferrocene in the main chain. Okay. Now we finish the ring opening polymerization of ferrocene to obtain the ferrocene in the main chain. Now we will go to another class of reaction that is called dehydrocoupling, which has been done in the University of Leipzig. What I have done, like phosphorus-based polymers of ferrocene derivatives. Okay. So there are many phosphorus-based polymer are there in the literature. Now we already studied these ferrocenophanes, polyphosphazines, all these things. So now we will talk about a different kind of polymer, that is polyphosphinoburens. Okay, this polyphosphinoburens, I will say some history about it. In United States, the research on this polyphosphinoburen started because this phosphinoburen not only can give you hydrogen gas, but also these polymer are very much useful to give you flame retardant material or flame resistant. Flame retardant material is what is kind of material which will not burn. Okay, if you have a um, paint paint of made of this polyphosphinoburen, if you paint it on a surface of a wooden surface, and if you put it onto the fire, it will not catch fire. Okay, but the wood, if you would have put it on the fire, it will immediately catch fire. But if you put this wood with made of paint of this polyphosphinoburens, it will not catch fire. Okay, so by this way you can imagine, like if we have lot of fire cases in trains and buses or the houses, if you don't made those kind of painting or of this kind of flame retardant material, then it would been very useful. We will not get so many loss of properties. Uh, so these polyphosphinoburens are interesting. You can introduce PB bond backbone and introduce lot of uh, side chains here. Okay, and if you see, this is a valence isoelectronic with carbon-carbon bond. Okay, so this is actually four valence electron is four carbon, and its carbon is four plus four eight. But here in this case you have five electron and here three electron. So five plus three is eight. So that's why it is called valence isoelectronic with carbon carbon. But one more interesting factor with this carbon carbon polymer, you will see there is no difference in electronegativity in between these two carbon. See, but here due to their different material, they definitely have different electronegativity, and due to this electronegativity difference, it is actually electron sharing in this sigma bond is not equal like carbon carbon. So they a little bit, so p delta plus b delta minus, this kind of electron sharing is observed. So conductive, it can be conducting also. So now we will discuss about dehydrocoupling technique. Okay, that is used to obtain this polymer. Okay, uh, this is our um, any element you can think about, but with hydride, hmm, AH or EH. And when we these two hydrogen is removed, you get H2 gas. The element bond formation is there. But you have to remember here, this H2 cannot be formed if both are hydridic. One should be H minus and one has to be a little bit H plus. So one element should have acidic in character and one has in basic in character. Otherwise, H plus H minus type of formation will not be there. Okay. And by the removal of the small molecule, formation of the polymer is nowadays very, very interesting factor. Okay. Nowadays, it has become very interesting to form a polymerization or element-element bond by removal of small molecules like hydrogen, CH4, water. This kind of polymerization techniques are very important. But this is called dehydrocoupling because hydrogen is removed in this process. In previous days, it has been actually seen that uh, this dehydrocoupling was possible using just heating. You use primary phosphinoburen compound you get and you heat it very high temperature like 250 degrees centigrade or 300 degrees centigrade. This much high temperature you need to get the polymerization. If you heat them, this hydrogen is removed and you get this polymer. But the problem was that in that way, it you need very high temperature for industrial purpose. If you want to industrialize this compound to produce this compound, this is not so good method because you lose a lot of heat energy. You need a lot of electric energy or coal energy to get those heat. And one more thing is that by this way, you are not able to get a very linear polymer. Okay. Uh, like it was like controlled way was not possible. And in this case, rhodium catalyzed dehydrocoupling has been introduced by Professor Ian Manners in around 1990s. This kind of polymerization already started around 1955, 1960, this time. Okay. 56, 58, 60, like this way. This United States Army, they started research on this. But later on, around 1990, Professor Ian Manners of University of Bristol, they have started uh, this reaction using a rhodium catalyst. And they found that here the heat was needed almost like 250, 300 degrees centigrade. Here the heat is needed only 60 degree or 90 degree, like this type of temperature was needed, not much. So it was they can reduce the temperature almost 200 like degree, 200, 150 degree. So it was very much useful research by Professor Manners. So I used this rhodium catalyzed dehydrocoupling to obtain polymers of ferrocene derivatives. Okay. So here the phosphorus, you can see that this is R group is there. If this R group is replaced by ferrocene moiety, as I mentioned earlier, that we can introduce different properties if we can introduce a different materials. So we can get a metal containing polyphosphinoburens, okay, or ferrocene containing polyphosphinoburens. So how to introduce metal into the polymer? Either you get a metal connected with a polymerizable group and you polymerize it, you get this kind of polymer. Or you have the polymer having such a group like a X where you can introduce like this type of metal with leaving group Y and into leaving of XY, you can introduce the metal as a side chain. Okay. So this kind of possibilities or this kind of techniques can be there. We already a little bit discussed. So when you introduce metal, as we discussed already, that can give you electrical conductivity, that can introduce magnetic properties into your polymer, that can give you thermal stability, nonlinear optical activity, superconductivity, many other things are possible. So these are the this is the three things we will discuss in like introduction of different things. Okay. Now we will go to the reactions firstly. So in this synthesis one, we first can get ferrocene with directly ferrocene with this N equal to 1 or 2 with ferrocenyl phosphinoboren. We have to obtain phosphinoboren first. So I have introduced a ferrocene group and a polymerizable group. This is the polymerizable group. This will polymerize. Okay. So I will get the ferrocene already introduced into the monomer. So as a result, I will get the polymer. So this is the technique. You can see I get this is a little bit wrongly mentioned here. Actually, this is not BH3THF. So here, first we have the polymer. First we have the monomer that pH2. We BH3. We have to get the BH3THF, and then if we polymerize it with rhodium catalyst. So this is a little bit wrongly written here. This is a mistake. When I share the slide, I'll change this. Okay. So then this pH to BH3, when I have the pH to BH3, that is polymerized to obtain the polymer. So that is shown here. So here I first get those primary phosphine and introduce a BH3THF. So it goes to the here nitrogen and then comes to here. So if I polymerize now, if I start polymerize now, this dehydrocoupling, I will polymerize this pH to BH3 unit and eventually I get the polymer like this. Okay. So I hope you understood and these are all characterized properly. So see here, I showed you one example. So I have the first CH2, pH2, BH3 and using rhodium catalyst and when I removal of hydrogen gas, I get this polymer. Now, the main question will come into your mind. So how to characterize those compounds? Okay. How I characterize those compounds? So the characterized was very interesting for me. So I used gel permeation chromatography to see the molecular weight of this compound. Okay. So this is almost 10,000 Dalton. And one more unit I wrote, Polydispersity Index, that is 1.6. So to inform you about the polydispersity index, I will say uh, mm, it is the ratio of weight average molecular weight by number average molecular weight. This is the theoretical part. But to understand, you have to remember that polydispersity index, if it is 1, okay, means all the polymer chain into your material, into your that sample, all chains are of same length. Then only you will get polydispersity index of 1. If it is more than 1, like 1.2, 1.3, in my case it is here 1.6, it means that you do not have all the polymer chain in the same length, little bit different. Okay, and that's why it goes beyond 1. Okay, so only polydispersity index of 1, this kind of material or this kind of polymer only possible by our nature. They only can make a very controlled polymeric chain. In the real artificial synthetic way to obtain or like polydispersity index 1 is almost near to impossible. But there are some examples definitely is there, but it is impossible. Okay. So this is the polydispersity index of this compound, and see this is the phosphorus 31 NMR of this compound. Okay. Here phosphorus this is the dehydrocoupled coupling, dehydrocoupled polymer. So there is no coupling of the hydrogen is observed. But this too is actually due to the PB coupling. Okay, PB coupling generally boron is I equal 3 by 2. So I expect 4 peaks. So there is actually 4 peak here. One is here in the hump. 2, 3, and 4 is here. Okay, so I can only see these two. And then when I polymerize it, you see it became broad, but it is coming almost in the same region. Okay, so this is the hint that you get a polymer out of phosphinoburens. Hmm. And when you can see when I did the coupled NMR of phosphorus, coupled means I coupling with phosphorus with hydrogen. Hmm. So two hydrogen, like 2 into half in plus 1, like 3. So I get 3, 1 is to 2 is to 1 type of coupling. Okay. But here, see, very interestingly, here phosphorus is connected with only one hydrogen. So I will get a doublet. So I get a doublet. So through NMR also we were able to characterize this compound. Okay, so nicely characterized in those polymers, and we are very happy that we are able to get a ferrocene containing polymer. Now we face a very big problem when we wanted to introduce a planar chiral ferrocene compound. And here we can see that we can obtain these different kind of polymers. And this is why? Because uh, this is due to this kind of um, this why yes here. So here we have NMA2 BH3 and PH2 BH3. See, just to want to say one thing here, when I have NMA2 and PH2, okay, if I go to the little bit older slide here, when I have this NMA2 and PH2, if I want to give BH3, phosphorus and nitrogen both have electron or lone pair electron to donate. Okay, so nitrogen will also competition with phosphorus. Okay, but as we see, nitrogen is connected with 3 alkyl group. It is more prone to give the first to boron. So when I added boron, I see the boron is go to the nitrogen first, and the next boron, when I add a second equivalent, it will go to the phosphorus. So I obtain this compound. So similarly, you can see here. So when I do the dehydrocoupling reaction for the next step, polymerization, I have here hydrogen, also here hydrogen. And by these two hydrogen can connect and can give you this kind of polymer. This is a normal polymerization. But we have to remember that I also have a boron with connected with nitrogen, and this hydrogen is also hydridic in nature. Yes, hydridic in nature. So this can also be get coupled and give you this kind of little bit haphazard and branched polymer. So that's why I didn't get very good NMR peak for this compound, but we have this kind of very long range polymer. And also you can see the 2.4 polydispersity index means it is goes beyond 2, not only 1. It was before it was 1.6, it is 2.4. Means I have lot of different chain length was there, like small one, bigger one, longer ones, all different kind of chain lengths are there. So the distribution was not narrow, broad distribution of polymer chain was there. So then I tried to stop. Okay, so so that's why I first did this ionization and phosphine, and then I blocked this nitrogen donor side, and then I got this compound, and we have crystal structure of this compound. But interestingly, this compound became insoluble in almost all solvents. So the polymerization, I used solid state technique. Okay, so I just heat this compound in presence of rhodium catalyst, and I got this kind of polymer out of it. And with this, as it is not soluble, I am not able to do the NMR for the liquid state. So I did the solid state NMR, and I found, I showed proof that it has been polymerized eventually. So lot of other proofs are there. And here, when I did the thermogravimetric analysis here, in this case, for the monomer, it decomposes around 250, but the polymer is stable until almost 350. Okay, so you can see. One interesting factor I would like to show you here, that you see, even after 900 degree, 800-degree temperature, the polymer, the percentage is, see here it is almost 50% of monomer, and the polymer is almost 60%. Okay, 60-70% is remaining. Huh? Like 30% is already lost. The other, it is remaining product is there. Hmm. So these are very interesting factor for the material, and we did some TEM analysis of this compound, and we found that it might be the boron phosphides, ceramic material obtained from this. So that's what I was talking about. That when you're talking about flame retardants, it means if you heat them, even in the presence of oxygen or air, it will not burn. It will not stay. So after heating 1000 degree, it 80%, 70% is remaining. Okay. Now for this polymer, actually it is 60%. For the other polymers I prepared like this, those these polymers, okay, these polymers, when I heat it, it was almost 80% was remaining, 20% was lost. Okay, so this is very interesting factor for the, it can be used as a flame retardant material. So recently we have collaborated with Professor Fami with this, with having our polymers. It has been published in last year. Professor Fami in Germany. He was working with electrospinning. So they took our ferrocene polymers, and they have electrospin with polyethylene oxide and polystyrene polymer, and they found this kind of material. And it has been observed by them that when polyethylene oxide or polystyrene is there, it decomposes easily. But when this they blended with, or I'll say electrospin with ferrocene polymers, with these two polymers, okay, one and two, they have observed that it has been increased the thermal stability of this compound manifold. Okay, so you can have a look into this paper to get the real applications of those polymers from our group. So mostly I actually covered almost all the polymer related product what I wanted to talk about. As I have little bit time, so I will show you one more technique little bit about regarding the uh, phosphinoburens. That is called Dehydrator Crosstalking. This is the technique in our group we have invented. This is something like this is I whatever I showed you that I started with the primary phosphine. Primary phosphine means phosphorus have two hydrogen in it. So this is primary phosphine borans. You heat it, you with catalyst, you get the polymer. But whenever you start with a secondary phosphine, when phosphorus has one hydrogen with R2, you will always end up with this dimer or the cyclization happens. So our target was to start with the secondary phosphine boron, because here actually two R group is there. So I can introduce two ferrocene or two different kind of products I can introduce here. So it can be very interesting. So in that case, I actually, that's why I wanted to start it with the secondary phosphinoboron to get a polymer. But the main problem was there, it never polymerized. It never give you polymer like this. It will always stop here, and if you give little bit heating, it is actually a cyclization happens. Okay. And we have to stop the cyclization. And by which I have to stop? I was thinking that by which way I can stop this cyclization. If I have something here like this, if this pH is there now, so if I can remove this pH group, H hydrogen here, it will not be able to cyclize with another one. Okay. So by which way I can do this? If I can give you a coupling or dehydro cross coupling with this. Okay. Then one phosphorus end is having no hydrogen. See here, phosphorus having no hydrogen. This normal coupling, dehydro coupling will give you this product. But if I have cross coupling between these two, so this will give you this kind of product which is having no hydrogen. Now you can polymerize it. Okay. So toward this process, we got success in combining uh, with this ferrocene-based polymer with these two kind of tertiary phosphine, and we were able to find it out. So that's what I was talking about, no, planar chirality and other chirality. So here you can see this compound when it is dehydrocoupled. This is a secondary phosphine. Okay, pH is there and one hydrogen is there. And when I have polymerized it, it actually gives me a this kind of having hydrogen. But this compound you can see having two chiral center, and it means it will give you a diastereoisomer. And whatever, and these are the diastereoisomers. You can see two enantiomer, two and four, a total four enantiomer and two diastereomers pair is there, and which in the P31 NMR, 31 phosphorus NMR, we have seen this product. Okay, this is the mixture, and after we separate it out, we found this. Okay, through normal column chromatography, these compounds are stable in air, and we through column chromatography we can really separate those two diastereomeric pair, and we can get this compound pure. Okay, see, this is the pure compound having only one peak. Uh, and crystallized, this has been crystallized, and of course we have bond length and bond angles here mentioned. This is the boron 11 NMR. Okay, because we have two boron environment. Here is one PB is there, na? P boron BH2, and this is here BH3. BH2 and BH3 environment is there. That's why two boron peaks are there. And now we have tried to get the polymer out of it. And yes, I just show you one more reaction where with this tertiary butyl derivative pH based, I use tertiary butyl and N-butyl, this N-butyl, and this tertiary phosphinoboren decoupled, cross decoupled it, and we got this is the polymer. See, this is the NMR whatever we obtained in the beginning, phosphorus 31 NMR. Then from this, actually, uh, we have through column chromatography, we would be able to separate it out. Pure compound, 18 compound. And you can see these three peaks. If you can recognize those peaks, these are nothing but the dehydrocoupled product of this compound. Okay, so when I do the cross coupling between these two, I also obtained a dehydrocoupled product in between this ferrocene compound. Okay, so I hope you understand. This is the same technique with another material. And how I can explain you the cyclization? How can I stop the cyclization? See here that this, when I have the dehydrocoupled product, I have a hydrogen at the end of the phosphorus, and we have the BH3, and they can couple and they can form the cyclic product. But in my product, you can see there is no hydrogen here. I have used the tertiary phosphines, and as a result, I do not see any coupling is possible. So I can get this kind of change. So only selectively. So I do not have much time, so I think we will just shortly I'll explain this. This is the something that we wanted to introduce a chirality into the phosphorus, into this polyphosphinoburens. For that, I have obtained this ugizamine. I have started with ugizamine, that is a chiral phosphine, ferrocene phosphine amine already, and then I introduced a phosphine boron and obtained this this polymer. And but it was very difficult actually in practically to obtain this kind of things, because we have nitrogen and phosphorus, both are comparable. They both try to donate to the boron to obtain the boron, so it was very difficult. situation. So now I have to somehow introduce something that cannot be donated. The boron will not go to here. Boron will only go to here. And by this is possible by which way? If I something introduce with phosphorus as a group, which will definitely go to the, which will be more donor compared to this secondary amine. Actually, when I introduced I'll not go into the details of this chirality factor. I'll just want to inform you one thing at the end, that somehow I got a product here. You can see with this glycamine, when I have the tertiary group attached to this phosphorus. This is the boron NMR. This is the for the nitrogen boron NMR peak, and this is the phosphorus boron peak. Okay. Whenever I have tertiary butyl group attached with the phosphorus, I do not see any peak here. Okay. Only phosphorus boron product was obtained extensively. So this was a very interesting factor we have done with theoretical studies, that in hexane or THF, this phosphorus boron for this compound, tertiary butyl product, is very stable compared to the nitrogen boron adduct. So we have proved that. And yeah, so I just came to the last slide. So all these things, I'll definitely have to say thank you to my professor, like which I did my PhD work with her. She's very kind and helpful and supporting in all the ways. This is the picture which we see visited India once. And I was in Trivandrum, Kerala. There we took the picture. And this is Professor Ian Manners, who is working on he's a chair in the Marie Curie scholarship. So he's very influential person and also very busy person working on polymer chemistry. There are a lot of books. And Professor Pitsnick is in University of Kassel. He also has some collaboration work with me. And I would like to thank also Sikkim University, UG University Grant Commission, and Indian Chemical Society for different grant process, because now I am working on other polymer techniques, coordination of hello bismuths that I have not talked about now at all. So maybe in future, if I get time, we can talk about. So, and lastly, I would like to thank all of you for your presence, listening to me, and thank you, Dr. Vitri, for inviting me and the organization, and to the university, all the faculties to really allow me to talk to you. And it was very nice to give a presentation. Thank you very much.
Yes, Dr. Souvik.
Yes. So if you have any questions, the students, you can ask me, or we can talk about all those. So did you understand all the things? Yes, yes, please.
Thank you, Dr. Souvik, for your nice lecture about ferrocene, and also about inorganic polymer. We have a lecture in bachelor and master also about inorganic polymer.
Yes, yes.
Partly was delivered by Dr. Sayakti and partly by me. Yeah. And I think some of the students from Dr. Sayakti are joining now.
Okay. Yeah, actually, I also taught this inorganic polymer here in the university. So I thought, okay, maybe
Okay.
So it will be interesting.
And yeah, it's interesting. There are many applications of organic polymer, and I saw that in your lecture, especially with the silicon and also with the ferrocene and other kind of inorganic polymer.
Yes. Actually, we can also make a block copolymerization. We can introduce silicon with ferrocene. There are a lot of applications with those. Even in the ferrocene-based polymers are very interesting. They are used in detecting sugar in the blood nowadays in the medical facility. You can see there are a lot of applications.
Yes. And some of your synthesis was done using the hydrocoupling reaction, yeah, Dr. Sophie.
Yes, yes.
Maybe can you so again about the hydrocoupling reaction? Here is Dr. Sayakti joining the lecture of organometallic chemistry in our department. Welcome, Dr. Sayakti.
There's some sound I cannot hear. What?
Yeah, maybe can you show again about the dehydrocoupling reaction in synthesizing the silicon-based polymer?
Yes, yes, yes. This dehydrocoupling techniques actually we can use to obtain this to obtain get Si-Si bond. Okay, so polysilanes can be obtained by using these dehydrocoupling techniques. And actually, I
Yeah.
work.
What kind of catalyst you use?
They are actually you can use zirconium based catalyst or titanium based catalyst like CP2TiCl4 or CP2TiCl CP2 titanium Cl or H2. This kind of catalyst you can use. I actually in the presentation I have one zirconium based catalyst I showed you. That is that we can use also.
Okay. And maybe the audience, would you ask some question? The audience, the student, let's ask some question about India. You can ask also.
Yes, yes, students, you can ask.
In film is very.
So I will be very much interested to
The
if I
Indian
can.
film is very famous here.
Yes, yes. Yeah, India and Indonesia, we are very close in culture. Our habit of food, if we remember, we have a lot of nice food in Germany. We used to cook.
Yeah, there is a
Okay.
question from student in the chat box.
There is question from student.
Yes, student,
Yeah.
please.
I will read. Yeah. I will read Dr. Souvik, yeah. As previously mentioned, that polythiazole has metal-like characteristic. What about the physical properties of of this polymer, yeah, such as hardness, flexibility, and so on? Yeah. And is it possible to make polythiazole as an electrode?
Oh, polythiazole is actually very interesting compound, sulfur nitrogen based compound. I think it is there are some applications all made of like to make like electrode material because it actually behave like a metal. So and very
Yes.
highly conducting material. So it is already is used. So
And the
the
second question, what's about the characterization technique using spectroscopy to distinguish the ferrocene and other ferrocene derivative?
yeah, I think the characterization technique actually we have to discuss more because now in polymer chemistry it is very much used like I'll say some people may doubt how you characterize how much molecules. So the characterization techniques is very important to for the ferrocene. I'll say if it is possible to do the NMR like I did the NMR, okay. If, if you have ferrocene, definitely it will be as I said, it can be a little bit colored. Okay, normally the polymers are on like colorless compound. It will definitely have a color, and also the NMR. If you for the proton NMR, you will definitely see a peak near about 4. That is the C cyclopentadienyl ring, and also you have to remember that you have a iron compound there. Okay, so you can use spectroscopic techniques most or like different kind of techniques uh, which can be used also to detect those mm,
And
ferrocene
I saw
conductor.
that
Yes, yes.
I saw you present the TEM images, yeah, of your ferrocene residue after you
Mm.
heat it, and then you analyze the compound of this ferrocene residue, and you make like TEM image. What is the importance of that?
What you mean? What I didn't understand. Maybe can you repeat?
I saw that you present a TEM image. in your
TEM,
slide.
TEM image. Yes, yes, yes.
What is the importance of that? What do you want to show actually?
Yes, actually, when we saw that that in TG analysis, I found like almost 80% or 60% is remaining my product after hitting 90 degree. Generally, that time we definitely wanted to see what is this compound. Okay, so we did the elemental analysis also, if there is any carbon, hydrogen, nitrogen is there or not. So, but we didn't find any carbon, hydrogen, nitrogen. Then we saw, okay, to what is the characterization techniques we can do. There is TEM image, what I can see any nanoparticles has been formed or not. Okay, so for that actually,
Okay.
we did those TEM images. Actually, it has been done in when I was there in Ian Manner's group.
And then the question, is it possible to bind the ferrocene to the surface of nanoparticle like that?
Yes, yes, definitely. I think there are a lot of works is going on this actually to bind, because if you have nanoparticle and if you have some kind of ferrocene based polymer, suppose I just if you remember that slide, in the slide that we have ferrocene having a pendant group like amine, NME2, NME2, all this. So if this kind of pendant group is there, which can really bind to the nanoparticle, okay, mm, surface, that is very interesting. So there are a lot of also like already there are some literature is there where platinum gold nanoparticle is bonded with ferrocene polymers. So
Okay,
it is
thank you.
very interesting. It is very interesting actually. Thank you. I think this is very interesting book and very
Can you
recent work.
continue your work? Yeah. Dr. Souvik, can you continue your work or research on ferrocene in India?
Research work, yes, yes, definitely. I think now actually I am working on hello bismuted type of compound that I have not discussed about here. So this type of research work I am doing now. If we get opportunity, we can also, the research work will be definitely, I'll continue.
Are there any question about this ferrocene and about inorganic polymer, or maybe about the reaction? If someone
I
to
want
know,
to ask.
yeah,
Yes, yes,
please, Prof.
yes, please,
Fenty.
yes, Professor Pandey, please.
Yeah, thank you, Dr. Pandey. It's a very nice talk, and I learned a lot because I never know before about the inorganic polymer. And in my, it's I mean, on your slide, I was reading your slide that inorganic polymer is better than organic polymer. Yeah.
That's good. That I actually
I was so surprised because I never knew it before.
yes, yes. So that is, so actually I succeed to give you this impression that inorganic polymer is better. I always fight with the organic people.
And is there any type of metal that can be introduced in inorganic polymer? Because you choose ferro, yeah? Why do you choose ferro, and are there any type of organic inorganic polymer? I mean,
Yes, yes, yes. There are a lot of other kind of metals are introduced, even like I say like this. I showed you this tin. SN is there, like platinum, germanium, palladium, gold. Uh, there are a lot of other metals are there to be introduced or already introduced into the metal, into the polymerization, into the polymer. But for me, I have chosen ferrocene because ferrocene is, I found it very interesting a molecule, because you see it is a sandwich compound, and iron is there. Iron can go to the redox activity Fe2, Fe3. This redox activity I can introduce, and this cyclopentadienyl ring. These rings are very interesting. And all the known chemistry about benzene ring. I know benzene reacts, how it reacts with other material. other elements. So those reaction experience I can use to introduce any substitution into the cyclopentadienyl ring. I can introduce chirality, huh? Plana chirality. I can introduce a lot of other properties, and that's why in this I choose ferrocene, because it is really interesting compound and it can give you metal, CP ring, all these different kind of varieties are there. Non-linear optical chromophore it is a colored compound. It can give you color. So by the looking, you will understand that your reaction is going on. Will happen, because this is very interesting for our research purpose. Now, if I can see something that okay, my reaction is almost is going, so it is good, um, good feeling. So it is very interesting. That's why I choose iron, or you can say ferrocene, for the polymerization.
Actually, I want to ask more.
Yes, 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 please, please.
You saw the color or different color for your polymer. Yeah? Is it already polymer or it's
No,
just
no, no.
not
Those are
polymer yet? Yeah.
not yet. They are like the monomers, ferrocenophanes.
When it's become polymer, it is soluble in water and then making changing in color, something like that. Or?
No, so these are actually the solid compound. When I dissolve it in hexane or like the proper solvent, and then I see the color. But these are very strained compound. Okay, like they are like this. So in this case, actually, what happened? They are very strained. If I heat it, or if I give some UV radiation, they get polymerized and give you this ferrocene inside the main chain. It is not like hanging outside. It is the ferrocene will be in the inside the chain.
Yeah, yeah. I have synthesized some compound. It's the color is colorless, but when I add some metal, it's the color become
Yes, yes, yes.
changed.
That is the interesting part of inorganic chemistry. You will see the color as soon as you introduce some metal due to this either DD transition or metal to ligand charge transfer. But in this case, generally, that definitely it is a DD transition.
Yeah, and you synthesize compound by making ring closer, yeah, in your structure.
Yeah, yes, yes. Shall I go to the slides for you better or?
Oh yeah, yeah, it's okay. Yeah.
Okay. Then. So which one? No, just give it to me. I think you wanted to mean which compound? Let's check. This structure
Yeah,
or this
yeah,
structure?
yeah, yeah. Bring closer.
This one, this one?
Yeah, this one. I think
Hmm.
it's yeah.
So tell it again or this one?
It's okay. It's okay.
It's okay. This one?
So this is a P. What is it? P.
Maybe I.
Post. Yeah.
A cyclic product, you mean? I think this is, you mean,
Yeah. So P. What is it? P. pH. You mean phenyl? Yeah.
pH. No, I didn't get it.
Phenyl. Yeah. You
Family.
mean it's phenyl?
Phosphine boron, I didn't get it. What do you mean?
Yeah.
No, no, what I didn't get it.
Oh,
Can you please?
phosphine. Yeah.
Phosphine.
Phosphine. This one phosphine with hydrogen. Yes, phosphor with hydrogen. Phosphine.
Yes, phosphine. This is phosphine boron product because phosphorus is having a hydrogen. Okay. So generally phosphine is called, like if you say phosphine, that is pH 3 molecule phosphine. it is very reactive compound, very reactive with air. They get easily hydrolyzed with water. Uh, but this is called primary phosphine. Primary, and because you have two hydrogen atom attached to this phosphorus, and this is called secondary phosphine because I have one hydrogen is attached here.
Yeah. Okay. Thank you very much for your explanation.
Thank you, thank you. I hope I was able to
Yeah, it
So
explain.
opened my mind that organic polymer is better than
Yeah, that's what
organic
I think. No,
polymer.
I think that's why it is better that if we say directly, like we say, like in front of you, then I could have betterly understood or betterly explained to you. But this technology is sometimes it is difficult to understand. Like
Yeah.
so, that's why it is better to if we overcome this COVID situation and go directly to your university, or you can come here so you can talk more. Yeah.
Thank you for your invitation.
yes, thank you, Prof. Enti, for the question. And the next question is coming from Dr. Sayakti. Yeah. We see the textbook. It tells a lot about ferrocene, how the character of ferrocene bind to late metal and early metal. Yeah. Does it provide stability that is significantly different?
Character of ferrocene binds to late metal and early metal. Does it provide stability that it okay. That is significantly different? Ferrocene binds to
I
late.
understand the question,
Okay.
Dr.
Yes. Yeah. So mm, see the ferrocene itself has a metal. No, let me check again. The let metal. It is talking about metal. Yes, metal. So the thing is that ferrocene already have a iron. Okay, in the ferrocene. So when we want to bond a metal, so it is definitely for the late transition metal like rhodium. These are very good in binding. Okay, but because we have some example where the ferrocene and some ruthenium rhodium compound is bonded with the like in the side arm, like in the ferrocene in the cyclopentadiene ring. So for the late metal, it is I'll say it is very good in binding compared to the early metals. Because also you have to remember that iron and the metal what you want to introduce, they should not be repulsive, or they should not be positive character. Okay, they should, if you introduce something like I'll say like bismuth or some sodium or little bit like this sodium potassium like this kind of compound that will actually this positive character can repulsion with each other. So they we have to introduce a metal which have a acceptance of this Fe2 plus. I think it is understandable, or is it? Did you wanted to ask?
Any feedback, Dr. Hekti? Oh, thanks.
Okay.
Thanks for the answer.
Okay.
And Dr. Souvik, in general, what is the stability of ferrocene compound? I mean, ferrocene derivative and the ferrocene compound. Is it air stable, or it should treated under nitrogen or something like that?
No, ferrocene is very much stable compound in air. You do not have to do not have to store it under nitrogen or any other things you need. It is also it is very cheap. You can buy it in a big amount, and you can do the research on this. So it is not it is not difficult to work with the ferrocene. It also react, I said it is react like aromatic rings. So you can use all those your experience with phenyl ring reaction, you can use to introduce. But in some cases, when in some reaction, ferrocene is not a problem, but in some reaction you have to involve with n-butyl lithium. to lithiate it to make a
Yes.
substitution on the ring. So that kind of things are you need a little bit. But other reactions like addition of CHO, COCH3, if you wanted to introduce this kind of product or ferrocinyl aldehyde, this kind of product is also available in market. You can make C-based compound, and there are a lot of things are possible, which you can use really normal ambient temperature, ambient condition.
Okay, thank you. Are there any questions for the audience, from the students?
Yes, yes, please. Also, I think you can share my email IDs, or we can have questions. We can talk.
Yes. Okay, Dr. So Prof. Andy should
Yes.
leave because he
Thank.
has another meeting.
Okay.
It's
Okay.
very
Yes. Yes.
Maybe one more question, yeah. For biomedical
I'm
application.
sorry, Dr. Pandey, I have something, another
No.
meeting.
No. Yes. 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 I understand.
Thank you very much. Hopefully we can meet someday.
Yes. 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 Thank you. Definitely. Thank you. It was very nice to meet you. Really. It was
Nice to
very
meet
good.
you.
Thank you. Thank you. See you again.
We continue again, yeah. And Dr. Souvik, for the biomedical application, what the people or the researcher do with ferrocene, what the modification they do for the biomedical application so far?
Actually, truly speaking, I do not have much work on these biomedical applications. I work on material science industry, but I will say that I shared one picture. So I think it is mostly uh, mm, you can use some kind of element, like suppose this sulfomethoxazole type of compound, like the compound already known for the biological applications. This kind of compound you can introduce to the ferrocene moiety. Some amine, some
And so
amine
far,
compound. Yes, yes.
and so far, I know that you have many publication here about ferrocene derivative and then some reaction and so on. What kind of application that have you done so far?
See, the ferrocene-based chemistry I actually did in the Germany there. After that, I did some work, but it is not yet published. But I have did some electrospinning with other polymer, the polyethylene oxide, polystyrene. These compounds I have blended my already synthesized polymer with those polymers. Like I mixed them too by electrospinning. And because you have to remember that my polymer are all PB polymers, so they have some kind of positive and negative charge, like delta plus delta minus delta plus delta minus, like this, like so due to this they actually uh, um, can actually give a very kind of structure, I'll say, can attach, okay, can attach with any other having little bit polar material, or they have some kind of donor property, or not donor property, I'll say, like they have some kind of property they can attach because they have plus minus plus minus. They are not like neutral compound. So by this way, they with polystyrene and polyethylene oxide, this kind of compound, we got a very nice attachment to those polymer. And when I attach those ferrocene-based polymer with polystyrene and polyethylene oxide, we found the stability, thermal stability mostly, have increased. Okay, of those polystyrene polyethylene oxide, with just giving like 1 point like one like 50%, not 50%, it's a 30% to 20% of our polymer and 70% of the polyethylene oxide. And this kind of mixture, when they prepared, it is found that they are very stable. They become more thermally stable. And also one more, I'll say, like when I tried to do some ferrocene chemistry with some with a collaboration with biological people, and we have seen there is some antimicrobial activity with some ferrocene compound, but those are not polymers. Those are normal compounds.
Okay. Are there still questions from the audience?
Yes. So ferrocene is very nice compounds. You can try.
Student that come late can access this lecture through the YouTube channel. Yeah? We record this lecture and also link to YouTube channel from Himamia. Yeah, I will share the link.
Okay, okay.
Especially the class of organometallic chemistry.
Mm-hmm. Yes, yes.
Yes, here is the link.
Okay, this is the link,
Oh,
nah?
I forgot.
Oh.
Yes, yes. I forgot about the presentation. Jessica is there. Jessica, please make like Google form for this event to GFORM, yeah, for presentation. Untuk Jessica, tolong dibuatkan GFORM ya Jessica untuk presensi hari ini. Dr. Souvik, maybe you have motivation or you can share to students. Yeah, you have a lot of experience with chemistry, I think, and you get some scholarship to go abroad. Maybe do you have like motivation for our student how
Yes,
to be
yes,
a good
yes.
student and how to achieve some scholarship? Can you share it?
Yes, yes, definitely. If I'll get it and maybe I'll share it to you, or where you mean? In the
You can share here. I mean, you can share here what your motivation or how to become motivated. Yeah, to be motivated chemist.
no, at the moment, I think I do not have any link or something to share, but I think I will share it in future. Okay, maybe. I think there are a lot of.
Do you have like message?
I have.
I mean,
Uh-huh.
can you share with our student like just some words to be motivated in chemistry?
Yes, so for the students.
Yes.
Yes, yes. Hello, students. I have not seen any one of you in the in this online classes. I see only the blank screen. But anyway, it is very nice that you're there, and yeah. So I'm trying to see how many are there, or is there anyone I can see? I can see only 2 or 3 pictures actually. Okay. So I will say that chemistry, you are all in chemistry. So this is one of the most interesting part of the, I'll say, education, okay, or the study. Because chemistry is everywhere. If you love chemistry, I think you will find it in every single factors happening around us. And truly speaking, the next generation or next future is based on chemistry. It will be happening. Okay. So if you see that in agriculture, if we need food, if we need to wear, if we need color, fashion, everywhere, you can if you do research, if you can modify the things like in the electronic devices, the material, superconductivity, everything you can explore. Okay, so now you are in the BSc. If you are in the BSc, you still have time to select your research area, to find your interest. You can do whatever you want and select your area you want to do the research in future. And for the master student, I'll say you are already In some now you have to choose that you have to use the which research area you would like to do. Already, I think you have found it. So whatever the area you are doing, whatever the area it will give you a very high interesting future. I can assure you about that. So mm, do study and do properly, but you have to love the chemistry. Okay, I have done.
Okay, thank you. Thank you, Dr. Souvik, for the last session. I think I will present your certificate. Yeah.
Okay, okay.
I hope you see this. Yeah. Thank you for your time to give a lecture in our university or in our department. Yeah.
Okay, okay.
And for the audience, yeah, please open your camera and we will take picture together before ending the meeting. Yeah. Please open the picture or please open your video.
So now I can see some faces there. So yeah, so the students, I think I will say like you can see some when we were also student, we did hesitate a lot of things to ask a lot of questions or something. But I think you can definitely in future or sometime in email you can contact me. You can ask questions. Okay. So whatever it is, we will try to discuss.
And we can take picture together. Yeah. Please.
Yes, yes, yes.
Stop share here. One, yeah. Only some.
Is it working?
Okay. 1, 2, 3, yeah. And the slide number 2. One, two, three. Still so many black here. Black
Yes, yes.
faces without face.
Yeah, yeah. I
And
think it is
for person
also
who join this event, please fill the G form here for the proof that you are joining the lecture. That deliver here. The link is in the chat box here. Please fill the form. Thank Dr. Souvik. Many thanks again for your contribution to deliver the lecture in our department. Hopefully everything is fine in India and good luck for your career, for the research.
yes,
And hopefully we'll meet again
yes,
for
definitely.
another time. Yeah.
Yes, definitely, definitely. Thank you very much, Vitri, and also all the organizers here, professors. Thank you very much for inviting me.
Thank you, Dr.
Thank you.
Thank you very much.
Okay. I'm sorry.
I think you were in Leipzig. You were there, or
Who's Souvik?
Other
Bentar, Nih.
perspective. No, no. I think I think you. Now, one, I think faculty member from your group was there, no? In Leipzig.
No? Yeah, Dr. Fitria. Dr. Fitria. And what else? Dr. Heru. No, he. And
okay,
some of the students. Oh yeah, some of the
the
students were in Leipzig.
the,
Yes.
yes.
Hopefully someday we can visit India.
Yes,
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 after the
definitely.
COVID is over.
Yes, definitely. I think that is the motto that we can do some collaborative research and we can.
Okay.
I will share some if there is something like comes to like collab. There are a lot of program actually for doing this collaborative research exchange students.
Yes. For student who join this meeting, please fill the G form, yeah, as approved. And now as a moderator, I officially close this session, and we will meet again next week with the speaker from Mailand State University. He is working in the MOV area, yeah, Dr. Kif Mahlena. Yeah. Okay, Souvik, yeah, many thanks again, and see you next
yes,
next
maybe.
occasion, yeah.
Yes, yes.
In the future, hopefully.
Yes, yeah, definitely. Thank you very much,
Okay.
everyone. Shall I leave now?
Bye.
Yeah, bye.
Yeah, you can leave or you can stay. But the meeting is over actually.
No. I have to go somewhere. Okay. Thank you, everyone. Bye.
Bye.
Thank
you.
Bye. Thank you, Mr.
Bye.
Terima kasih
Terima
atas
kasih, Bu
kehadirannya
Fitri.
ya. Sami-sami Bu.
Thank you, Bu
Itu
Fitri.
kalau mau
ini saya
yang
juga lagi
yang dari
rapat
depan di
soalnya
YouTube.
Ini keluar masuk.
Itu kalau yang materi dari depan ada di YouTube, Bu. Di YouTube-nya yang saya share tadi, di Himamia itu. Terima kasih.
Anak-anak biar nikmatin yang di YouTube. Biar
terima
kan
kasih.
terlambat.
Sudah, Assalamualaikum. Waalaikumsalam. Jangan lupa presensi ya, adik-adik.